Water dominates the composition of liquids on Earth, including lakes, rivers, and oceans, as well as the composition of all living organisms. It is therefore an important fact that the physical and chemical properties of water differ greatly from those of many liquids of similar molecular structure, including in its complex changes with temperature and pressure. The macroscopic physical properties of a liquid can be classified into several categories, and water has unusual features in each of these. Thermodynamic properties include heat capacity, density, and the propagation of sound, and these relate to the type and arrangement of molecules in water. Transport properties include viscosity as well as thermal and electrical conductivity, and these describe the rate at which momentum, heat, and charge are transferred. While interface properties, like surface tension and refractive index, govern changes associated with the boundaries between different fluids. Many of the anomalous properties of water can be explained by its unique chemical structure. As a result of its angled shape, the charge distributions around the molecule are not symmetrical, even although the total charge is balanced. There is a slight negative charge located near the central oxygen atom, and a positive charge near the hydrogen atoms. Thus, the molecule has an electric dipole moment. This polar nature of the molecule allows for hydrogen bonding between water molecules, and also between water molecules and dissolved substances, solutes. This leads to the formation of lattices, clathrate cages, and polymers. Water is therefore a highly structured substance, although these structures form and reform on very short timescales of the order of 10 picoseconds. There are many consequences of this tendency toward a structured form. The structures are difficult to disrupt, leading to anomalously high melting and boiling points and to a large heat capacity relative to other liquids. In ice, the tetrahedral crystal structure contains many voids, so its density as a solid is significantly less than liquid water. As ice melts and warms, the molecules reorient and rearrange themselves into denser packing with fewer voids, helped by a slight bending of the hydrogen bonds. However, as the water further warms, the greater thermal agitation causes intermolecular distances to rise, acting to decrease density. This changing balance between the tendency to closer packing due to reorientation and the tendency toward greater spacing by thermal agitation gives rise to highly nonlinear changes with temperature, with maximum density at 3.984 degrees Celsius. The polar water molecules tend to form structures around ions called hydration shells. This greatly increases the solubility of many substances relative to that in other liquids by acting to separate the positive and negative ions. Electrical conductivity in natural waters is largely governed by salinity, although exact relationships depend on the chemical composition of the dissolved salts. Electrical conductivity is also highly dependent on temperature, increasing by about 1.9% for every degree increase in temperature, largely due to changes in viscosity. Conductivity adjusted to a set temperature, usually 25 degrees, is called specific conductance and is widely used in limnology as a measure of salinity. The density of water generally increases with increasing solute concentration. Thermodynamic equations of state have been derived for pure water and for seawater that allow this density and other physical properties to be computed as a function of temperature, salinity, and pressure. Dr. Rich Pavlovich is a professor of oceanography in the Department of Earth, Ocean, and Atmospheric Sciences at the University of British Columbia. His research addresses questions about the hydrodynamic functioning of lakes, fjords, and the coastal ocean. and he was a member of the international team that developed the thermodynamic equation of seawater, TEOS-10. Here he describes this set of equations and some of the limnological applications and limits.
TEOS-10 provides an accurate, thermodynamically consistent, and complete representation of all thermodynamic properties of seawater over a wide range of temperatures and salinities. These properties include density, sound speed, heat capacity, and many others. These equations can be applied to inland waters by substituting the absolute salinity term with the limnological salinity. In cases where the dominant anion is bicarbonate, the majority of inland waters, measurements of electrical conductivity can be used to estimate the ionic salinity, which will be about 60% greater than the absolute salinity of seawater of the same conductivity. Effects of non-conductive silicate must be handled separately. However, in lakes of high salinity and/or unusual chemical composition, detailed laboratory measurements may be required to estimate relationships between salinity, conductivity, and thermodynamic properties.
An example of this is here at Mono Lake, a soda lake in California with unusual mineral content. For hydrodynamic studies, it was necessary to develop an empirical equation of state by weighing known volumes of lake water at different dilutions. The density of most waters on Earth varies within a range of only 0.5%. But these small differences in density can result in pronounced stratification and convective water movements. Specific heat capacity is the energy required to raise a unit mass by 1 degree Celsius Kelvin at constant pressure. For water, this is about 4,200 joules per kilogram per degree Kelvin, which is very high relative to most substances. For example, 400 to 1,000 for rock and soil, around 1,000 for air, and less than 2,100 for ice. The daily and seasonal cycles of temperature in natural waters are therefore much smaller than those in the air above the water and the surrounding land. This affects local weather conditions, including daily onshore and offshore winds, milder winters and cooler summers near the water, and fogs that appear above the lake surface in fall. The viscosity of water is the resistance it gives to moving objects, and it decreases with temperature. Viscous drag affects planktonic life, which has developed a variety of ingenious propulsion mechanisms to overcome its effects. Viscous drag determines the sinking rate of small particles such as phytoplankton and the rise rate of small bubbles. The diffusivity of a substance in a liquid measures the degree to which that substance will disperse. Thermal diffusivity characterizes the spread of heat from warm to cold areas and is approximately 100 times larger than the molecular diffusivity of most dissolved salts in water. These molecular diffusivities differ from eddy diffusivities, which are derived from turbulent motions of the fluid that can disperse heat and salts at orders of magnitude faster rates. The large difference in molecular diffusivity for heat versus salt can give rise to instabilities that change the water column into a highly layered state in which profiles have a characteristic staircase appearance, with steps in both temperature and salinity. A striking example is known from saline Lake Vanda in Antarctica, where there is a double diffusion cell of convective mixing more than 20 meters thick, as well as many thinner, well-mixed layers, all protected from wind-induced mixing by the permanent ice cover of the lake. The intermolecular hydrogen bonding in water, balanced in all directions, is interrupted at the water's surface. The water molecules at the surface are subject to an unbalanced force directed inward toward other water molecules and also directed sideways. The resultant surface tension at the air-water interface is higher than for almost all other liquids. Certain organisms that would otherwise sink live at the air-water interface, supported by the surface tension of the water, and are collectively called the neuston. Refractive index is a measure of the speed of light in the substance, and it governs the change in direction of light rays as they propagate through a surface. Refraction at the water surface makes it difficult to view lake bottoms through a surface wave field, but also allows for a variety of flow visualization techniques in the field and laboratory. The refractive index of water is also responsible for many of the beautiful features seen in, on, and above lakes.